Before we begin, I need to tell you something that's going to shock you. Most YouTube videos about this story are completely wrong, not just dramatized. Wrong. They'll show you operational Spitfires with revolutionary contra-rotating propellers tearing through German formations during World War II. They'll describe combat missions that never happened. They'll fabricate dialogue and invent details that make great drama but terrible history. Here's what actually happened. And the truth is far more fascinating than the fiction. Welcome to History of World War II, where we don't do AI-generated content. We verify every fact, we show you the documents, and we tell you when we don't know something instead of making it up. If you're tired of clickbait history, you're in the right place. This is History of World War II, and today we're setting the record straight about one of aviation history's most ambitious experiments. The contra-rotating propeller system that could have revolutionized the legendary Spitfire, but arrived at exactly the wrong moment. If you're new here, subscribe now. We publish deeply researched World War II documentaries every week with no shortcuts and no AI narration reading Wikipedia. And to those already part of this community, thank you. Your support makes this possible. We read every comment and take your suggestions seriously. Now let's dive in. Act 1. The Impossible Problem. The Beast. Nobody could tame Southampton, England, late 1943. The Supermarine Aviation Works had been devastated by German bombing in 1940, operations dispersed across southern England. But by autumn 1943, production had recovered. Engineers were working on what should have been the ultimate Spitfire, the Mark 21 powered by the massive Rolls-Royce Griffon engine. The weather that October was typically British, grey, rainy, with winds gusting across Boscombe Down, where the Royal Aircraft Establishment conducted testing. Inside hangars, mechanics gathered around what should have been Britain's answer to every German fighter. The Spitfire Mark 21 looked formidable. Larger than earlier variants, strengthened fuselage, redesigned wings, 4 20mm cannons. On paper, perfect. But there was a problem. A massive, physics-based, seemingly unsolvable problem. The Rolls-Royce Griffon 65 engine produced approximately 1,850 horsepower at sea level. The original Spitfire prototype from 1936 had used a Merlin engine producing roughly 1,000 horsepower. Early Spitfires in the Battle of Britain used Merlins producing about 1,100 horsepower. The Griffon was nearly double that power. That power should have been revolutionary. It should have pushed the Spitfire past 470 miles per hour, faster than any German fighter. It should have given Britain absolute air superiority for the invasion of Europe. Instead, it created an aircraft that was borderline unflyable at combat speeds. Squadron leader James McKinnon pulled himself from the cockpit after a test flight on October 12, 1943, hands visibly trembling. Not from fear, though there was certainly that. From sheer physical exhaustion. He'd spent 40 minutes fighting an aircraft determined to kill him. His flight suit was soaked through despite the October chill. His shoulders ached from wrestling the control stick. His legs felt like rubber from constant heavy rudder pressure. Chief Engineer Malcolm Whitfield didn't need to ask how it went. He could read it in McKinnon's expression. "How bad?" Whitfield asked, though he already knew. McKinnon's Scottish accent grew thicker with frustration. "At 350 miles per hour, she wants to roll left so hard I nearly spun her. The torque from that bloody engine, it's like the propeller is trying to tear the nose off. Above 400? Forget it. No pilot could hold her straight in combat. You'd be so focused on flying you wouldn't see the Germans shooting you down." The numbers painted a grim picture. The Griffon 65 spun a 4-bladed propeller at approximately 2,000 revolutions per minute. That propeller, nearly 12 feet in diameter, was essentially a massive gyroscope generating enormous rotational forces. Newton's third law is unforgiving. For every action, there's an equal and opposite reaction. When that propeller spun clockwise at 2,000 RPM generating thrust, it also generated rotational force, trying to spin the aircraft counterclockwise with equal intensity. At low speeds, pilots could compensate, push harder on the rudder, use trim tabs. But as airspeed increased, aerodynamic forces multiplied exponentially. Think about holding a powerful drill. At low speeds, controllable. Increase the speed and torque becomes overwhelming. Now imagine doing that while conducting precision work, making split-second decisions, and avoiding someone shooting at you. That's what flying the Griffon Spitfire at combat speeds felt like. At 200 miles per hour, manageable. At 250, difficult. At 300, exhausting. At 350, dangerous. At 400, the aircraft became a trajectory rather than a machine responding to pilot inputs. Whitfield ran his hand along the propeller hub, feeling faint vibration even with the engine shut down. He'd been an aircraft engineer since the early 1930s. He understood the physics and the challenge. And he was increasingly convinced it might be unsolvable. The Germans have the same problem, Whitfield said without comfort. The Focke-Wulf 190 series suffers from significant torque issues, but they've learned to work around it through pilot training and tactical limitations. McKinnon shook his head sharply. Malcolm, we can't work around physics. This isn't about technique or training. At the speeds we need to achieve air superiority over Europe, this aircraft is simply unflyable. And if we can't solve it... He didn't finish. Everyone in that hangar understood the stakes. The Ministry of Aircraft Production had invested millions developing the Griffon engine. They'd spent additional millions redesigning the Spitfire's airframe. Production schedules called for hundreds of these aircraft within months. Factories had been retooled, supply chains established, workers trained. The Royal Navy desperately needed the naval Seafire variant to match American carrier-based fighters in the Pacific. British naval aviation had fallen behind, and the Griffon-powered Seafire represented the best chance to catch up. Failure wasn't just an engineering setback. It represented a potentially catastrophic gap in Allied air power at the war's most critical phase. Intelligence indicated invasion of France would happen in 1944. Air superiority over invasion beaches would be absolutely critical, and Britain's most advanced fighter was unflyable. Understanding the physics. Let me explain the physics, because understanding the problem makes the solution more impressive. Newton's third law. For every action, there's an equal and opposite reaction, not a suggestion. A fundamental law that cannot be violated. When the Griffon rotates the propeller clockwise at 2,000 RPM, the propeller pushes against air, generating thrust. But air pushes back. That interaction creates forward thrust, propelling the aircraft, and rotational torque, trying to spin the airframe. The propeller tries to spin the entire aircraft opposite to the propeller's rotation. At 2,000 RPM, that's 2,000 torque impulses per minute, 33 per second, creating constant rotational pressure on the airframe. In low-powered aircraft, this is manageable. The original Spitfire's 1,000 horsepower Merlin had torque effects, but within reasonable limits. Pilots learned to compensate during training, but torque doesn't scale linearly with horsepower. It scales exponentially. Double the horsepower and you multiply the torque problem by factors that compound as airspeed increases. At 200 miles per hour, aerodynamic forces on control surfaces are modest. Pushing harder on the rudder provides counterforce to balance torque. But at 400 miles per hour, air density and pressure create exponentially greater resistance. The rudder becomes less effective precisely when you need it most. Add the other demands of flying high-performance fighters, navigating, watching for enemies, managing engine systems, communicating, and the torque problem becomes not just difficult, but dangerous. Every high-powered fighter faced this challenge. American P-47 Thunderbolts with 2,000 horsepower radial engines. The Corsair with its unique inverted gull wing partly designed to manage propeller clearance and torque. German Focke-Wulf 190s. Soviet Lavochkin fighters. But the Griffon's combination of high power and relatively light airframe made the problem more severe than almost any other aircraft. The conventional solutions that failed. British engineering wasn't idle. Multiple teams worked on various approaches to mitigate torque. Every solution looked promising on paper. Every solution failed in flight testing. Attempt 1. Enlarge the vertical stabilizer logic was straightforward. If the problem is insufficient control authority, increase control surface area. make the rudder bigger, increase the vertical stabilizer, give pilots more leverage. Engineers redesigned the tail assembly, adding roughly 15% more area to the vertical stabilizer and increasing rudder size proportionally. Modified aircraft went into testing September 1943. Result: marginal improvement at best. At speeds above 350 miles per hour, the aircraft still fought the pilot. The larger tail added weight and drag. Performance actually decreased slightly. You'd gained minimal control improvement while losing speed advantage the Griffon should provide. Attempt 2. Modify engine mounting. The second approach focused on isolating torque reaction. If the engine's rotational forces could be prevented from transmitting into the airframe, maybe the problem could be reduced. Engineers designed sophisticated engine mounts with damping systems, essentially shock absorbers to absorb rotational energy rather than transferring it to airframe structure. This required weeks of design work and testing to ensure the mounting wouldn't create vibration problems or structural failures under combat stress. Flight testing began early October 1943. Result: negligible improvement. The torque reaction wasn't primarily transmitted through engine mounts. It was an aerodynamic effect acting on the entire airframe. Isolating engine mounting did nothing to address fundamental propeller torque physics. Additionally, modified mounting raised structural integrity concerns. Engine mounts must be absolutely solid to handle combat maneuvering, emergency situations, and crash landings. Introducing compliance created potential failure points. Risk wasn't worth minimal benefit. Attempt 3. Adjust propeller blade angles. The third approach examined the propeller itself. Propeller blades can be adjusted to take different-sized bites out of air. Decrease blade angle, reduce thrust generated, and you proportionally reduce torque reaction. This was the most promising conventional solution. By carefully adjusting blade pitch angles throughout the propeller's operating range, engineers could reduce torque without completely sacrificing performance. Flight testing showed measurable improvement. Torque effects decreased by approximately 20–25%. Pilots reported the aircraft was more manageable, though still difficult at high speeds. But there was an unacceptable trade-off. Reducing propeller thrust meant reducing aircraft performance. The Mark 21 now achieved about 420 miles per hour, instead of the design target of 470. You'd made the aircraft more flyable by making it slower. Given that the entire point of the Griffon was creating a faster, more powerful Spitfire, this defeated the purpose. You couldn't accept 50-mile-per-hour performance penalty just to make the aircraft manageable. At that performance level, the Mark 21 offered no significant advantage over late-model Merlin-powered Spitfires already in production. Intelligence pressure. German developments. While British engineers struggled, intelligence reports painted increasingly concerning pictures of German aircraft development. Ultra-decrypts, intelligence from breaking German Enigma codes, revealed that Messerschmitt was making rapid progress on high-speed Me-262 jet fighter variants. The Me-262 was already revolutionary. If Germans could refine the design and produce it in quantity, Allied air superiority could evaporate. Focke-Wulf continued development of their TA-152 high-altitude interceptor series. These combined powerful engines with pressurized cockpits and long-span wings, optimized for high altitude. They represented direct counters to Allied bomber formations depending on high-altitude operations for safety. Reports of German jet and rocket-powered experimental programs were even more concerning. The Me-163 rocket interceptor, despite limited operational utility, demonstrated German engineers were pursuing multiple parallel paths toward higher performance. Strategic implications were clear. The Allies couldn't afford to fall behind in fighter performance. Invasion of Europe would require absolute air superiority. Bomber formations needed fighter escorts that could dominate any German interceptor. Close air support for ground forces required fighters that could respond quickly and operate effectively over battlefields. Every month of delay in solving the Griffon Spitfire's problems was a month when British fighter squadrons operated with aircraft being matched or exceeded by German developments. Pressure on engineers intensified daily. This wasn't an academic problem to be solved when convenient. This was urgent strategic necessity with lives hanging in the balance. Enter Joseph Smith, the unconventional engineer. 15 miles from troubled Spitfire test flights, in the cluttered office of Rotol Air Screws Limited in Cheltenham, Joseph Smith worked late on a cold October evening in 1943. His desk was buried under technical drawings, slide rules, empty teacups, and pages of calculations in his precise handwriting. Smith was 42 years old, older than many engineers working on cutting-edge aircraft development. He'd started his career in the 1920s when aviation was still considered almost magical, when aircraft were fabric-covered wood frames with barely reliable engines. He'd watched the industry transform into something far more sophisticated, but he'd never lost his willingness to question conventional assumptions. His official role was propeller designer at Rotol, but that undersold his expertise. Smith understood propeller aerodynamics at a level few engineers in Britain could match. He'd designed propeller systems for Rolls-Royce that pushed boundaries of what manufacturing could achieve. He held patents on variable pitch mechanisms, blade profiles, and sophisticated control systems. His reputation was complicated. Ask 10 engineers about Joseph Smith and you'd get 10 different opinions. Everyone acknowledged his brilliance. His designs, when they worked, delivered performance exceeding predictions. But they also acknowledged his designs were often impractical, too complex, too demanding of manufacturing precision, too difficult to maintain in field conditions. Smith had a pattern: study a problem, identify what he believed was the optimal solution regardless of practical constraints, then work backward to figure out how to make it manufacturable. This approach produced brilliant results when successful, but also expensive failures when manufacturing challenges proved insurmountable. He'd been following the Griffon Spitfire program closely. He had contacts throughout British aviation, and the torque problem was common knowledge among engineers. Everyone knew about it. Everyone had opinions. Most engineers accepted that compromises would be necessary, that the perfect solution probably didn't exist within practical constraints. Smith disagreed. He believed the perfect solution existed. It would just require abandoning conventional assumptions about what was practical. The concept canceling force with force. The idea that would transform the Spitfire had been percolating in Smith's mind for weeks. It wasn't entirely original. Contra-rotating propeller systems had been theorized for decades, but nobody had seriously proposed implementing them on frontline fighters during wartime. The concept was elegant in physics. If torque from clockwise rotating propeller creates leftward rotational force on the airframe, add a second propeller rotating counterclockwise to create equal rightward rotational force. The two forces cancel each other. Zero net torque on the airframe. But that simple concept required solving multiple complex engineering challenges. You need to take single rotational output from the Griffon and split it into two contra-rotating outputs at precisely controlled speeds. This requires sophisticated gearbox with multiple gear stages, each machined to tolerances at the absolute limit of British manufacturing capability. The gearbox would handle enormous torque loads, 1,850 horsepower transmitted through mechanical components smaller than a standard automobile engine. Gear teeth would experience forces measured in tons per square inch. Any imperfection in manufacturing, any misalignment, any imbalance would result in catastrophic failure. Two propellers mounted on the same shaft, spinning opposite directions at high speed, must be balanced to extraordinary precision. If either propeller is even slightly out of balance, vibration will destroy the gearbox in minutes. For context, propeller balancing is measured in ounce-inches, rotational force created by 1 ounce weight at 1 inch radius. Propeller 11 feet in diameter spinning at 2,000 RPM must be balanced within a few ounce-inches to be acceptable. Smith's system would require both propellers balanced within fractions of an ounce-inch, maintaining that balance under combat conditions, temperature extremes, and constant high-power operation stress. Two propellers spinning opposite directions create complex aerodynamic interactions. The rear propeller operates in the forward propeller's wake. Tip vortices, miniature tornadoes of spinning air created by propeller tips, from both propellers interact in ways extremely difficult to predict without extensive testing. Done wrong, these interactions could create destructive resonance frequencies that would shake the aircraft apart. Done right, the rear propeller would recover some energy wasted in the forward propeller's wake, improving overall efficiency. The contra-rotating system would inevitably be heavier than conventional single propeller. That weight sits at the aircraft's most forward point, affecting center of gravity, handling characteristics, and structural loads throughout the airframe. Smith calculated the system would add approximately 200 pounds to the nose. For a fighter where every pound affects performance, that was significant. The additional weight would need to be offset by performance improvements to be worthwhile. Combat aircraft operate in harsh conditions. They're maintained by mechanics in field environments with limited tools. They need to be reliable enough to fly multiple missions daily. Any system too fragile or too complex to maintain in field conditions is useless regardless of performance advantages. Smith's contra-rotating system would require specialized maintenance procedures, trained technicians, and probably specialized tools. In wartime, these requirements compete with every other demand on limited resources. The calculations that changed everything. Smith spent 3 weeks in October and early November 1943 working through calculations that would determine whether his idea was feasible or fantasy. He started with basic torque cancellation requirements. The forward propeller would spin at a speed generating torque equal to what the standard Griffon installation produced. The rear propeller would spin opposite direction at a speed producing exactly equal and opposite torque. But it wasn't quite that simple. The rear propeller operated in the forward propeller's wake, which meant different aerodynamic conditions. Air hitting the rear propeller wasn't uniform. It was swirling, rotating, carrying energy from the forward propeller's passage. This actually presented an opportunity. If designed correctly, the rear propeller could recover some of that energy, extracting additional thrust from air that would otherwise just create turbulence. This meant the system could potentially produce more thrust than the sum of two independent propellers. Smith's calculations suggested approximately 15% improvement in thrust efficiency. That was significant. That would more than compensate for the additional weight of the gearbox system. Next came gearbox design. Smith needed to determine optimal speed ratio between the two propellers. This wasn't just about torque cancellation. It was also about maximizing efficiency, minimizing vibration, and staying within the operating range where propeller aerodynamics remained predictable. After extensive calculations, he settled on a 2-stage planetary gear train. The forward propeller would run at 1,825 revolutions per minute, roughly the same speed as standard propeller installation. The rear propeller would run at 1,475 RPM. The differential of 350 RPM would provide optimal torque cancellation, while keeping both propellers in efficient operating ranges. Gear ratios required were 0.77.1 for the forward propeller and 0.62.1 for the rear. These ratios would require precision machined gears with tooth profiles calculated to minimize wear and vibration. Weight calculations came next. The gearbox assembly, 193 pounds. 2 propellers instead of 1, approximately 85 pounds. Additional structural reinforcement, 22 pounds. Total system weight penalty, 300 pounds compared to standard installation. But the 15% efficiency improvement meant more thrust for the same engine power. That additional thrust would improve climb rate, acceleration, and top speed. Smith calculated that despite the 300-pound weight penalty, the aircraft would actually perform better overall. The numbers worked. On paper, the system was feasible. But aviation history is littered with designs that worked perfectly on paper and failed catastrophically in reality. Act 2. The build and testing, the meeting that nearly didn't happen. Smith needed Ministry of Aircraft Production approval to even attempt building a prototype. That meant convincing skeptical officials to allocate scarce wartime resources to an experimental system contradicting conventional engineering wisdom. Getting the meeting required calling in favors, leveraging professional connections, and essentially forcing his way onto the agenda through sheer persistence. The ministry had hundreds of proposals to evaluate. Resources were stretched impossibly thin. Default answer to any unconventional proposal was no. Smith's meeting was scheduled for November 15, 1943, in London. The timing was both fortunate and terrible. Fortunate because the Griffon Spitfire's problems were reaching crisis status, creating some openness to unconventional solutions. Terrible because that same crisis made officials extremely risk-averse about unproven technologies. The meeting room was imposing. Dark wood paneling, large windows overlooking bomb-damaged London. Long mahogany table surrounded by some of the most powerful figures in British aviation. Air Marshal Sir Wilfrid Freeman presided. Freeman had been instrumental in preparing the RAF for war, overseeing production programs that gave Britain enough Hurricanes and Spitfires to survive the Battle of Britain. He understood both technical and strategic dimensions of aircraft development. He was also notoriously impatient with proposals wasting his time. Director of Technical Development Sir Roy Fedden sat to Freeman's right. Fedden was one of Britain's most accomplished engine designers, having created Bristol sleeve valve engines powering multiple RAF aircraft types. His technical expertise was formidable, which meant he could identify flaws in proposals within minutes. Air Commodore Ralph Sorley represented operational requirements. Sorley had overseen fighter development through the Battle of Britain, working with designers like Reginald Mitchell and Sidney Cam to refine specifications for aircraft like the Spitfire and Hurricane. He understood what combat pilots needed and had little patience for engineering cleverness that didn't translate into operational advantage. Group Captain Peter Thornton rounded out the panel, representing maintenance and logistics. Thornton's job was ensuring that whatever aircraft entered service could be supported by RAF maintenance infrastructure. He'd seen too many brilliant designs fail because they couldn't be maintained in field conditions. Smith faced this panel with nothing but his calculations, his drawings, and his conviction that he was right. "Mr. Smith," Air Marshal Freeman began, his voice carrying formal precision of a man who'd conducted hundreds of these meetings. "We've reviewed your proposal for this contra-rotating propeller system. I must say, initial reaction from our technical staff has been skeptical at best. The consensus appears to be that your design introduces unnecessary complexity at precisely the moment when we need proven, reliable solutions." He gestured to a thick folder of reports that seemed to tower over Smith's modest collection of drawings. The message was clear. Established opinion was against this idea. Smith had prepared for this moment. He understood that he couldn't win with technical details alone. These men weren't just engineers. They were decision-makers balancing competing priorities in wartime. He needed to address not just feasibility, but necessity. "Sir, with respect, I believe the complexity of the system is precisely what makes it effective," Smith began, his voice steady despite pressure. "We're not simply adding components. We're fundamentally solving the torque problem that has made the Griffon engine unusable. At combat speeds, every conventional approach has failed because they're trying to manage a force that should be eliminated." Sir Roy Fedden leaned forward, expression skeptical. "Mr. Smith, your proposal calls for a gearbox system that would make this propeller assembly the most complex ever fitted to a fighter aircraft. We're talking about contra-rotating shafts, planetary gear reduction, precision timing that must remain perfect under combat conditions. The maintenance requirements alone could ground entire squadrons." This was the core objection Smith had anticipated. Complexity equals maintenance burden. Maintenance burden equals reduced operational availability. For combat aircraft, availability is everything. "The gearbox complexity is manageable with proper manufacturing tolerances," Smith responded. "De Havilland has already proven that complex propeller systems can be mass-produced reliably with their variable pitch mechanisms. Our system uses similar precision manufacturing techniques. The gear train would be sealed, lubricated, and designed for thousands of hours of operation between overhauls." He pulled out a detailed cross-section drawing of the proposed gearbox. "The system uses a two-stage planetary gear train with reduction ratio of 0.77.1 for the forward propeller and 0.62.1 for the rear. These ratios are calculated to cancel torque while maximizing thrust efficiency. The differential rotation speeds, 1,825 RPM forward and 1,475 RPM rear, create aerodynamic conditions where the rear propeller actually recovers energy from the forward propeller's wake. Group Captain Thornton, representing maintenance, shuffled through papers showing maintenance statistics for current RAF aircraft. Even if your system works mechanically, Mr. Smith, we're concerned about weight and balance. The Mark 21 is already heavier than previous Spitfire variants. Adding 200 pounds of propeller machinery could affect performance in ways we don't fully understand. We've seen other aircraft programs fail because weight penalties offset performance improvements. Smith had anticipated this objection. The weight penalty is real, sir, but the performance gains more than compensate. Our estimates show thrust increase of 15% combined with complete elimination of torque reaction. The aircraft would not only achieve its design speed of 470 miles per hour, but maintain controllable flight characteristics throughout the entire speed range. He pulled out flight test reports from the troubled Griffon Spitfire program. Current test flights show the Mark 21 becoming increasingly dangerous above 350 miles per hour. Pilots report needing sustained rudder pressure of 40 pounds or more just to maintain level flight. In combat conditions, that level of physical effort is unsustainable. Our system would extend safe operation well beyond 400 miles per hour, with zero torque reaction, requiring compensation. The room fell silent as officials absorbed implications. The Griffon Spitfire program represented millions of pounds of investment and months of development. Admitting that conventional approaches couldn't solve the torque problem meant accepting that either the program would be delayed or British fighter squadrons would operate aircraft with known limitations. Air Commodore Sorley broke the silence. Mr. Smith, intelligence reports indicate German aircraft development is advancing rapidly. We're seeing evidence of jet fighter development, high-altitude interceptors, and various experimental programs. The invasion of Western Europe, currently planned for some time in 1944, will require absolute air superiority. We cannot afford delays. We cannot afford experimental programs that might fail. He paused, letting strategic context sink in. Your reputation suggests that when you propose something unconventional, it's worth considering. But I must ask directly, are you absolutely certain this system will work? We cannot afford another failed modification program. The stakes are too high. This was the moment Smith had been working toward. Every calculation, every drawing, every hour of work came down to this question. Was he certain? Sir, I stake my career on it, Smith responded without hesitation. The physics are sound, the engineering is achievable, and the performance gains are exactly what the Royal Air Force needs. The Spitfire Mark 21 with contra-rotating propellers will be the fastest, most maneuverable fighter aircraft in the world. Freeman exchanged glances with colleagues, clearly calculating risks against potential benefits. The ministry had to balance desperate need for improved fighters against reality, that experimental programs consumed resources that could be used for proven designs. Very well, Freeman said finally. We'll authorize a limited development program, 1 prototype installation, full flight testing, complete performance evaluation. But understand, Mr. Smith, if this system fails to deliver on your promises, or if it delays Mark 21 production by even a month, the consequences will extend far beyond your career. This is your one opportunity to prove that unconventional thinking can solve problems that conventional engineering cannot. As Smith gathered papers, Fedden added final caution. Mr. Smith, you'll have access to our best manufacturing facilities and whatever resources are necessary. But you'll also be under constant scrutiny. Every delay will be questioned. Every technical problem will be evaluated for program continuation. The ministry cannot afford to continue experimental programs indefinitely when production aircraft are desperately needed. Walking out into damaged London streets, Smith understood exactly what he'd committed to. He had perhaps 3 months to design, manufacture, and prove a propeller system that contradicted every conventional assumption about fighter aircraft design. Success would vindicate his approach and potentially transform British air power. Failure would end his career and leave the Griffon Spitfire trapped with problems nobody could solve. The stakes couldn't have been higher. Air Commodore Sorley broke the silence. Mr. Smith, intelligence reports indicate German aircraft development is advancing rapidly. We're seeing evidence of jet fighter development, high-altitude interceptors, and various experimental programs. The invasion of Western Europe, currently planned for sometime in 1944, will require absolute air superiority. We cannot afford delays. We cannot afford experimental programs that might fail. He paused, letting strategic context sink in. Your reputation suggests that when you propose something unconventional, it's worth considering. But I must ask directly, are you absolutely certain this system will work? We cannot afford another failed modification program. The stakes are too high. This was the moment Smith had been working toward. Every calculation, every drawing, every hour of work came down to this question. Was he certain? Sir, I stake my career on it, Smith responded without hesitation. The physics are sound, the engineering is achievable, and the performance gains are exactly what the Royal Air Force needs. The Spitfire Mark 21 with contra-rotating propellers will be the fastest, most maneuverable fighter aircraft in the world. Freeman exchanged glances with colleagues, clearly calculating risks against potential benefits. The ministry had to balance desperate need for improved fighters against reality, that experimental programs consumed resources that could be used for proven designs. Very well, Freeman said finally. We'll authorize a limited development program, 1 prototype installation, full flight testing, complete performance evaluation. But understand, Mr. Smith, if this system fails to deliver on your promises, or if it delays Mark 21 production by even a month, the consequences will extend far beyond your career. This is your one opportunity to prove that unconventional thinking can solve problems that conventional engineering cannot. As Smith gathered papers, Fedden added final caution. Mr. Smith, you'll have access to our best manufacturing facilities and whatever resources are necessary. But you'll also be under constant scrutiny. Every delay will be questioned. Every technical problem will be evaluated for program continuation. The ministry cannot afford to continue experimental programs indefinitely when production aircraft are desperately needed. Walking out into damaged London streets, Smith understood exactly what he'd committed to. He had perhaps 3 months to design, manufacture, and prove a propeller system that contradicted every conventional assumption about fighter aircraft design. Success would vindicate his approach and potentially transform British air power. Failure would end his career and leave the Griffon Spitfire trapped with problems nobody could solve. The stakes couldn't have been higher. 6 weeks of manufacturing impossibility authorization came through formally November 18, 1943, 3 days after the meeting. Smith immediately began mobilizing resources, calling in favors, and leveraging every professional connection built over 20 years in aviation. The first challenge was the gearbox. Smith needed precision gear-cutting capabilities already monopolized by existing military production programs. Every machine shop in Britain worked at maximum capacity, on contracts scheduled months in advance. Getting priority access required written authorization from the ministry itself. Smith contacted James Morrison at Bristol Aircraft Company's precision machine shop in Filton. Morrison was one of few people in Britain who could achieve the gear-cutting tolerances Smith's design required. Tooth profiles machined to within 0.001 inches, gear faces polished to mirror finishes, assembly tolerances measured in thousandths of an inch. "Do you want me to stop current production work for an experimental program?" Morrison asked when Smith explained what he needed. "Do you have any idea how many contracts that will delay?" "I have written authorization from Air Marshal Freeman," Smith replied, pulling out official documentation. "This is priority 1 status. Whatever you're working on, this takes precedence." Morrison studied the authorization, then looked at Smith's technical drawings. His expression shifted from annoyance to professional interest as he recognized the complexity. "Contra-rotating propellers for the Griffon Spitfire," Morrison said slowly. This is the torque problem solution everyone's been talking about. You're actually going to try building this? Not trying, Smith corrected. Building, and it needs to be perfect. Any imperfection in gear cutting, any misalignment, any imbalance, and the system will fail catastrophically. Morrison spent an hour reviewing drawings, calculating cutting paths, determining which machines would be needed, and in what sequence. Finally, he looked up. 6 weeks, you said? For a gearbox this complex with these tolerances, under normal circumstances, I'd tell you it's impossible. We'd need 12 weeks minimum, probably 16 to be safe. We have 6 weeks, Smith repeated. The ministry won't authorize more time. If we can't deliver a working prototype by early January, the program will be canceled, and resources will shift to conventional solutions. Morrison nodded slowly. Then we work nights. We work weekends. I'll pull my best machinists off other projects. But understand, if this fails, it's not just your career on the line. My team will have delayed critical war production for an experimental system that didn't work. Gear cutting began November 22nd. Each gear required multiple operations: rough cutting, heat treatment for hardness, precision grinding, polishing, inspection, reassembly, testing. The planetary gear train required 9 precision gears plus main input and output shafts, each machined to tolerances pushing limits of 1940s manufacturing technology. Meanwhile, Smith worked with Rolls-Royce on propeller design. The blades themselves were less complex than the gearbox. Rolls-Royce had been manufacturing precision propeller blades for years, but balance requirements were unprecedented. 2 propellers, each 11 feet in diameter, each with 4 blades, all balanced as a system within fractions of an ounce-inch. The forward propeller needed independent balance. The rear propeller needed independent balance. Then the entire contra-rotating assembly needed balance as a unit. This required specialized balancing equipment that didn't quite exist yet. Smith's team had to build custom test rigs capable of spinning both propellers simultaneously while measuring vibration with extreme precision. Robert Harrison, Rolls-Royce's chief balancing technician, led this effort. Harrison had been balancing propellers since the 1920s, starting with wood propellers on civilian aircraft and gradually advancing to sophisticated metal propellers on modern fighters. But he'd never attempted anything like Smith's system. Each propeller individually, I can balance to within 1 ounce-inch, Harrison explained during their first meeting. That's our standard precision, but your system requires both propellers balanced as a unit, which means accounting for how they interact aerodynamically. That's something I've never done before. Smith pulled out calculations showing vibration analysis. If either propeller is more than half an ounce-inch out of balance, the system will generate destructive vibrations at operational speeds. We need both propellers perfect, and we need the system as a whole to be perfect. Harrison studied the numbers, his experienced eye recognizing immediately how difficult this would be. We'll need to hand-finish each blade, start with rough balance, then progressively refine by adding or removing tiny amounts of material until we achieve the precision you need. This is watchmaker-level work on components that weigh dozens of pounds and spin at 2,000 revolutions per minute. Propeller work began early December, running parallel with gearbox manufacturing. Each blade was individually weighed, measured, and adjusted. Blades were then assembled into propellers and tested on spin rigs. Adjustments were made. The propellers were tested again. More adjustments, more testing. By Christmas 1943, the project was running behind schedule. Gearbox manufacturing had encountered problems with heat treatment. Some gears had warped slightly during hardening and needed remanufacturing. Propeller balancing was taking longer than anticipated because extreme precision requirements meant tiny adjustments, followed by hours of testing. Smith spent Christmas Day in the workshop, working with technicians who'd volunteered to give up their holiday to keep the project moving. The ministry had already sent 2 inquiries about timeline status. Everyone understood that further delays would result in program cancellation. We need this finished by January 15th to maintain any chance of hitting the February flight test window. Smith told his team December 28th. That gives us 18 days to complete manufacturing, assembly, balancing, and initial ground testing. It's possible, but only if everything goes right from here forward. Gearbox assembly was completed January 8, 1944. Morrison's team had worked essentially around the clock for the final 2 weeks, with machinists sleeping in shifts in the workshop rather than wasting time traveling home. The finished unit weighed exactly 193 pounds, machined from high-strength steel alloys, and assembled with precision that would have been considered impossible a decade earlier. Initial testing on a bench rig showed promising results. Gears meshed smoothly. Oil pressure remained stable. Vibration levels were acceptable. But bench testing wasn't the same as operational conditions. The real test would come when the gearbox was mounted in an aircraft and subjected to actual flight loads. Propellers were completed January 12th. Harrison's team had spent over 300 hours on balance refinement, progressively approaching the impossible precision Smith required. Final balance testing showed both propellers within specification, forward propeller balanced to 0.4 ounce-inches, rear propeller to 0.3 ounce-inches, combined system to 0.5 ounce-inches. These are the most precisely balanced propellers ever manufactured in Britain, Harrison said during final inspection. Possibly in the world. If this system fails, it won't be because of propeller balance. The first test, February 23, 1944 Spitfire, Mark 21 serial number RK958, was selected for experimental installation. This particular aircraft had logged approximately 40 hours of flight testing with standard propeller system, so its flight characteristics were well documented. Any changes in performance would be clearly attributable to the contra-rotating system. Installation took 10 days, much longer than anticipated. The gearbox required modifications to engine mounting structure. The dual propellers required reinforced propeller shaft housings. The entire nose section needed rebalancing to account for additional weight forward of center of gravity. By early February, the modified Spitfire was finally ready for ground testing. The aircraft sat in a hangar at Boscombe Down, looking subtly different from standard Mark 21s. The contra-rotating propellers created an optical illusion. Your eye wanted to see a single propeller, but kept catching glimpses of the rear propeller behind the forward one, creating a disorienting layered effect. Chief Test Engineer Michael Lithgow supervised the ground-running program. Lithgow had been with the Royal Aircraft Establishment since the early 1930s, testing everything from fabric-covered biplanes to Britain's most advanced experimental aircraft. His experience made him conservative. He'd seen too many promising systems fail during testing to take anything for granted. "We'll start with low-power runs," Lithgow explained during the pre-test briefing February 15th. "Engine idle, then gradual power increases while monitoring gearbox temperature, oil pressure, and vibration. If everything remains within parameters, we'll progress to higher power settings." The first engine start revealed immediately that this wasn't a standard Spitfire. The sound was different, still recognizably a Griffon engine, but with a complex harmonic overtone created by the two propellers spinning at different speeds in opposite directions. It was almost musical, a layered drone that seemed to pulse and shift. Low-power testing proceeded smoothly. Gearbox temperatures remained stable. Oil pressure held steady at 60 pounds per square inch. Vibration levels were acceptable, though higher than a standard single-propeller installation. But as power increased, a problem emerged. At approximately 1/800 engine RPM, a resonant vibration developed that was clearly outside normal parameters. Instruments showed the entire propeller assembly vibrating at a frequency suggesting potential structural issues. Lithgow immediately ordered power reduction. The vibration damped out as engine speed decreased below 1,700 RPM. "We have a harmonic resonance problem," Lithgow said grimly, studying instrumentation data. "At specific engine speeds, the two propellers are creating interference patterns that amplify rather than cancel vibration. This is exactly what I was worried about with this system." Smith studied the data, his mind racing through calculations. This harmonic issue wasn't something he'd anticipated in design work. The propellers were precisely balanced individually, but their interaction was creating unexpected vibration at specific frequencies. "We can adjust gear ratios," Smith proposed. "If we change the speed differential between propellers, we can shift the resonant frequency away from normal operating ranges." "That would require disassembling the gearbox and remanufacturing gears," Lithgow countered. "We don't have time for that. The ministry expects flight testing to begin within days." Smith shook his head. "We can't flight test with this vibration present. If it manifests during high-speed flight, it could destroy the aircraft structurally. We need to solve this now, even if it means delay." After 2 days of analysis, Smith identified a solution. By adjusting blade twist distribution on the propellers, slightly altering the angle of blades along their length, he could change aerodynamic forces in ways that would shift the resonant frequency. This wouldn't require gearbox modifications, just propeller adjustments. Harrison's team spent another week refining propeller blades, making tiny adjustments to twist distribution, rebalancing, testing, adjusting again. By February 20th, modified propellers were reinstalled and ground testing resumed. This time, the resonance problem was largely eliminated. Some residual vibration remained at 1/800 RPM, but within acceptable limits. More importantly, vibration didn't appear at higher engine speeds where the aircraft would actually operate during flight. Lithgow signed off on flight testing to begin February 23rd, but his notes included caution. Ground testing suggests acceptable vibration characteristics, but aerodynamic loads during actual flight may reveal additional resonance issues. First test flight should proceed with extreme caution, with pilot prepared for possible structural vibration, requiring immediate power reduction and emergency landing. Squadron leader Jeffrey Wellham had been informed 3 days earlier that he'd be piloting the first test flight. At 24, Wellham had already accumulated remarkable experience, nearly 800 hours in various Spitfire variants, combat time over Britain, France, and Malta, and assignment to Boscombe Down's elite test pilot program. But experience didn't eliminate nervousness when climbing into an aircraft with completely unproven propulsion system. "How confident are you in this system?" Wellham asked Smith directly on the morning of the 23rd, standing beside RK-958 in early morning light. Smith met his gaze steadily. "The engineering is sound, the mathematics is correct, but this is the first time anyone has flown a contra-rotating fighter aircraft in combat configuration. You're going to discover things we can't predict." It was an honest answer, which Wellham appreciated more than false confidence. "If I experience significant vibration or control problems, I'm bringing her back immediately," Wellham said firmly. "I won't push through dangerous conditions just to complete a test card." "Understood," Smith agreed. "The goal is learning, not heroics. Bring it back safely and tell us what you experienced." At 9:15 a.m., Wellham completed cockpit checks and signaled for engine start. The Griffon fired with its characteristic deep rumble, immediately joined by that complex harmonic from the contra-rotating propellers. Even sitting still on the ground, you could feel this wasn't a standard aircraft. Ground control cleared Wellham for taxi at 9:22. The Spitfire moved smoothly, the propeller system showing no unusual characteristics during low-power operations. But Wellham was acutely aware that everything changed once you advanced to takeoff power and left the ground. "Boscombe Control, Test 27 requesting clearance for takeoff," Wellham radioed at 9:28. "Test 27, you're cleared for takeoff. Wind 210 at 8 knots. Good luck." Wellham positioned RK-958 on the runway center line and took a moment to review his mental checklist one final time. Every Spitfire pilot learned during training that you pushed hard right rudder during takeoff to counter the propeller's left-turning tendency. It was fundamental, instinctive, something you did without thinking. He advanced throttle to takeoff power, expecting to need significant right rudder input. The Spitfire tracked absolutely straight down the center line. For a moment, Wellham was so disoriented he almost overcorrected. His training screamed that the aircraft should be veering left. His hands and feet were positioned to counter a force that wasn't there. It was profoundly disturbing, like expecting to catch a heavy weight and finding it weighed nothing. He reduced rudder input, trusting the aircraft to maintain direction on its own. RK-958 continued straight and true, accelerating smoothly. At 85 miles per hour, Wellham gently pulled back on the stick, and the Spitfire lifted cleanly into the air. Boscombe Control Test 27 is airborne, Wellham reported, his voice carrying an edge of surprise he couldn't quite suppress. The takeoff characteristics are remarkable. Zero left-turning tendency. The torque cancellation appears to be working exactly as designed. Climbing through 1,000 feet, Wellham began noticing the first problem. The aircraft felt heavy, sluggish. He was using significantly more power than expected to maintain reasonable climb rate. Where a standard Mark 21 would climb at 2,000 feet per minute using 75% power, RK-958 required nearly full throttle to achieve the same performance. By 3,000 feet, he was genuinely concerned about climb performance. This wasn't slightly worse than predicted. This was significantly degraded. Leveling at 6,000 feet, Wellham reduced power to cruise settings and was immediately surprised. Despite poor climb performance, the Spitfire felt remarkably stable in level flight. At 280 miles per hour, an airspeed where standard Griffon Spitfires would be fighting the pilot constantly, RK-958 flew hands-off. No torque reaction requiring rudder input, no tendency to roll. Just smooth, steady flight. Wellham experimented with gentle turns, steep banks, rapid direction changes. The aircraft responded with agility that seemed impossible for such a powerful fighter. The elimination of torque reaction had restored legendary Spitfire handling. Boscombe Control, Test 27. Wellham radioed. Handling characteristics at cruise speed are exceptional. Best Spitfire I've flown in terms of stability and response. The torque cancellation is completely effective, but climb performance remains a concern. Test 27 understood. You're cleared for speed envelope testing per your test card. Exercise caution approaching high-speed regime. This was the critical test. Smith's entire concept depended on the contra-rotating system, allowing the Griffon Spitfire to achieve high speeds while maintaining controllable flight characteristics. Wellham advanced throttle gradually, watching airspeed increase. 300 miles per hour, 320, 340. The aircraft remained stable and smooth. At 350 miles per hour, Wellham tensed slightly. This was the speed where standard Griffon Spitfires began experiencing severe torque-induced control problems. RK-958 flew perfectly straight and level. No unusual forces on controls, no tendency to roll, just fast, stable flight. 360 miles per hour, 370. Still smooth. Then, at approximately 375 miles per hour, Wellham felt it. A faint buzzing sensation through the control stick, like the aircraft was vibrating at very high frequency. It wasn't severe, it wasn't immediately dangerous, but it was wrong. He pushed slightly faster, 380 miles per hour. The vibration intensified dramatically. The control stick was shaking hard enough that maintaining solid grip required concentration. The instrument panel blurred, making it difficult to read gauges accurately. Through his seat, Wellham could feel the entire airframe resonating. This is destructive vibration, he realized with cold clarity. If I push faster, something is going to fail structurally. Boscombe Control, Test 27 experiencing severe vibration above 370 miles per hour. Wellham reported, his voice professionally calm despite adrenaline spike. Reducing power immediately, returning to base. He pulled throttle back, slowing to 300 miles per hour where vibration damped out completely. His heart rate gradually returned to normal as he confirmed the aircraft was structurally sound and responding normally to controls. Landing at 9:58 a.m. was routine, but Wellham's post-flight assessment would determine the fate of Smith's program. As he climbed from the cockpit, his expression told Smith everything before any words were spoken. The contra-rotating propellers worked brilliantly, until they didn't. Asset 3, Redemption and Reality. 3 weeks to save everything. The emergency meeting at 11:30 a.m. was grim. Lithgow, Smith, several ministry officials, and Air Commodore Sorley, who had driven from London immediately upon receiving the preliminary report. Sorley got straight to the point. Squadron Leader Wellham, please provide your complete assessment. Wellham stood. Sir, the contra-rotating propellers completely eliminated torque reaction during takeoff and throughout low to medium speed flight. Below 300 miles per hour, the aircraft's handling was exceptional, possibly the best I've experienced in any Spitfire variant. Murmurs of surprised interest from the assembled engineers. However, Wellham continued, above approximately 370 miles per hour, the aircraft experienced severe vibrations that made further speed increases impossible. The entire airframe was shaking so violently I feared structural failure. Additionally, climb performance was significantly degraded. We required nearly full power to achieve climb rates that should have been possible at 75% throttle. Smith felt each word like a physical blow. 6 months of work, his entire reputation, producing an aircraft that performed brilliantly at low speeds, but became uncontrollable precisely when maximum performance was needed. Sorley's expression was calculating political consequences. Mr. Smith, your calculations presumably accounted for aerodynamic forces. How do you explain this discrepancy? Smith had spent 2 hours analyzing the same question. Sir, our calculations were based on static ground testing and wind tunnel data. The interaction between 2 contra-rotating propellers in actual flight, particularly at high air speeds, creates aerodynamic phenomena extremely difficult to predict without flight testing. The propeller tip vortices appear to be creating destructive interference patterns at specific speeds. He pulled out fresh calculations. When the forward propeller's vortices interact with the rear propeller at certain frequencies, they amplify rather than cancel, creating resonance that grows exponentially with airspeed. The question now, Sorley said grimly, is whether these problems can be solved within reasonable time frame, or whether we should abandon this approach entirely. Smith refused to accept defeat. Sir, I believe the vibration problems can be resolved through modifications to propeller blade design and gearbox timing. The fundamental concept remains sound. We simply need to eliminate the aerodynamic interference causing destructive resonance. Wellham surprisingly supported Smith. With respect, sir, the aircraft's handling below 370 miles per hour was remarkable. If Mr. Smith can solve the high-speed vibration issue, we could have an aircraft that combines the Griffon's power with handling characteristics exceeding any fighter currently in service. Smith seized the moment. The vibration analysis suggests the problem lies in the relationship between propeller blade angles and rotational speeds. By adjusting gear ratios to alter the speed differential between forward and rear propellers, we can shift the harmonic frequencies away from critical resonance points. Lithgow studied calculations with careful attention. The modifications Mr. Smith describes would require approximately 3 weeks of machine shop work, remanufacturing certain gearbox components to change reduction ratios, plus another week for rebalancing the entire system. Additionally, we'd need to modify blade twist distribution on both propellers to reduce tip vortex interaction. We could have the aircraft ready for second phase testing by mid-March. Sorley calculated timelines against competing priorities. Mr. Smith, you have one more opportunity to prove your system, but understand that this represents the absolute limit of our patience with experimental approaches. If the second test flight fails to demonstrate clear improvements, we will abandon the contra-rotating propeller program entirely. Is that clear? Perfectly clear, sir, Smith responded. The second test will succeed. The modifications began immediately. Smith's team worked with Morrison's machine shop to remanufacture critical gearbox components, changing planetary gear ratios from original 0.77.1 and 0.62.1 to new ratios of 0.85.1 and 0.75.1. These changes would alter propeller speeds to the tighter differential Smith believed would eliminate resonance problems. We're essentially redesigning the gearbox from scratch, Morrison told Smith during a midnight meeting February 26th. Every component needs to be reevaluated for stress. Every assembly needs rebalancing. Every interface needs verification. We're doing this in 3 weeks instead of the 3 months it would normally require. Smith understood the pressure. I know what I'm asking, but if we don't solve this now, the program dies. We solve it now or we don't solve it at all. Machining work proceeded around the clock. Teams of machinists worked in shifts, machines running essentially 24 hours a day. The ministry had authorized overtime pay and priority access to materials. Simultaneously, Harrison's team worked on propeller modifications. Blade twist distribution needed alteration throughout the length of each blade. Subtle changes to angle progression from root to tip that would reduce tip vortex strength while maintaining thrust efficiency. By March 10th, the modified gearbox was complete. New gear ratios manufactured, assembled, tested on bench rigs, and certified ready for flight operations. Modified propellers were completed March 14th. Each blade hand-finished, balanced, assembled into propellers, balanced again, then assembled as complete contra-rotating system, and balanced one final time. Harrison's notes showed 380 hours spent on propeller work alone. Installation began immediately. By March 16th, RK-958 sat in the hangar with rebuilt propeller system, looking externally identical but fundamentally different in details that mattered. Ground testing. March 17th showed immediately that something had changed. The complex harmonic sounded subtly different, still layered, still unusual, but somehow more controlled. More importantly, the resonance vibration that had appeared at 1,800 engine RPM was gone. The system ran smoothly through the entire power range, all parameters within specifications. Lithgow reported after 2 hours of increasingly aggressive ground testing. Gearbox temperatures stable, oil pressure nominal, vibration levels acceptable throughout power range. Whatever you changed, Mr. Smith, it appears to have worked, at least on the ground. March 18th, 1944, the flight that proved everything. The morning brought almost unnaturally perfect weather. Clear skies, calm winds, unlimited visibility. Wellham approached RK-958 with cautious optimism, tempered by vivid memories of his previous flight's violent conclusion. The modifications tested well during ground running, Lithgow told him during pre-flight briefing. But we both know that doesn't guarantee anything at high speed. If you experience any unusual vibration, any control anomalies, bring her back immediately. Understood, Wellham replied. But I'm going to push past 370 this time, assuming conditions allow. We need to know definitively whether the modifications solved the vibration problem or just moved it to a different speed range. Smith was present, but remained uncharacteristically quiet. Everything, his career, his reputation, months of work by dozens of people, would be determined by what happened in the next hour. Engine start at 10:10 a.m. The sound was different from the first installation, though Wellham couldn't quite identify what had changed. Takeoff clearance at 10:15. Once again, the profoundly disorienting sensation of a Spitfire that tracked perfectly straight without rudder input. But climbing through 1,000 feet, Wellham immediately noticed dramatic difference. The aircraft was climbing enthusiastically, eagerly, using only 80% power. Where the first installation had felt sluggish and heavy, the modified system was delivering the performance Smith had originally predicted. Boscombe Control. Test 27 climbing through 8,000 feet, Wellham radioed. Climb performance is significantly improved. Handling characteristics remain excellent. Requesting clearance to test speed envelope. Test 27, you're cleared for speed testing. Exercise extreme caution approaching previous problem areas. Wellham leveled at 10,000 feet and began methodical exploration of the speed range. 300 miles per hour, smooth and stable. 325, still excellent. 350, no unusual vibrations. Now came the critical test. At 370 during the first flight, vibration had begun. By 380, severe enough to force emergency return. 365, 370, 375. The aircraft flew perfectly, no buzzing through controls, no instrument blur, just smooth, fast, stable flight. 380 miles per hour, the speed where he'd aborted the first test. Still smooth. 390, 400, 410 miles per hour. The Spitfire felt more stable than conventional fighters at half that speed. Boscombe Control. Test 27 has achieved 410 miles per hour with no adverse handling characteristics, Wellham reported, allowing genuine excitement into his voice. The aircraft is completely stable and responsive. This is remarkable performance. Whatever modifications were made, they've worked perfectly. From the control tower, Smith watched through binoculars as his modified Spitfire carved precise turns against blue Hampshire sky, the contra-rotating propellers transforming the massive power of the Griffon engine into speed and agility that seemed to mock the limits of aviation physics. Wellham continued testing for another 30 minutes. High-speed dives. The Spitfire exceeded 450 miles per hour without compressibility problems. Tight turns at maximum power. The aircraft combined agility of earlier Spitfire variants with raw performance of the Griffon. Recovery from stalls and spins, completely predictable and benign. Landing at 11:32 a.m., Wellham's expression announced success before he spoke. "Gentlemen," Wellham said, looking directly at Smith, "what you have created is not simply an improved Spitfire. This is the finest fighter aircraft I've ever flown. The combination of speed, handling, and controllability exceeds anything in current service with any Air Force in the world." Air Commodore Sorley approached Smith with expression transformed from skeptical authority to genuine admiration. "Mr. Smith, I believe congratulations are in order. Your contra-rotating propeller system has exceeded our most optimistic performance predictions. The question now is how quickly we can begin production modifications for operational squadrons. The truth history forgot. And here's where we need absolute clarity about what actually happened next, because this is where most YouTube videos completely fabricate the story. Did operational Spitfires with contra-rotating propellers see combat in World War II? No, absolutely not. The successful test flight on March 18, 1944 proved Smith's system worked. The engineering was sound. The performance was exceptional. Everything Smith promised had been delivered. But proving a concept and mass-producing combat aircraft are completely different challenges. By March 1944, Britain's aircraft manufacturing operated at maximum capacity. Every factory ran multiple shifts. Every supply chain was optimized for specific production configurations. Every worker was trained on specific procedures. Making significant changes to established production required cascading modifications through the entire industrial system. The contra-rotating propeller system required specialized manufacturing that simply couldn't be implemented quickly. The gearbox demanded precision machining beyond what most aircraft production facilities could achieve. Propeller balancing required equipment and expertise that didn't exist in production environments. Maintenance procedures were completely different from standard systems. Most critically, the timeline didn't work. The ministry faced a brutal choice: delay production of conventional Griffon Spitfires by 6 months or more while retooling for the contra-rotating system, or continue building aircraft with known limitations but proven reliability. In March 1944, with invasion of Europe scheduled for the next few months, Britain needed fighters immediately. Not next year, not after retooling. Now. The ministry chose production over perfection, and given strategic reality, it was probably the right decision. What actually happened? Here's what the historical record shows. Several Spitfire Mark 21 airframes were converted to contra-rotating propellers after the war for continued evaluation. These test aircraft accumulated significant flight time and proved the system's operational viability. But they never entered squadron service. The Seafire 47, the naval variant designed for carrier operations, did receive production contra-rotating propellers. But this happened in 1947-1948, well after World War II ended. Some Seafire 47s saw combat during the Korean War in the early 1950s, where the contra-rotating system proved valuable in carrier operations. Various post-war aircraft adopted contra-rotating propellers, benefiting from engineering work Smith pioneered. But the iconic image of contra-rotating Spitfires dueling with German fighters over Europe during World War II, that's fiction. This doesn't diminish what Smith achieved. He solved a genuinely difficult engineering problem brilliantly. But the solution arrived at the wrong moment. Too late to affect World War II, early enough to influence post-war development. That's not failure. That's the reality of technological development during wartime. The legacy that endures Smith's work influenced aviation for decades. The gearbox design directly influenced post-war turboprop development. The vibration analysis became standard practice throughout aerospace. Understanding propeller aerodynamics advanced the entire field. Manufacturing precision pushed British capabilities forward. The Tu-95 Bear bomber uses contra-rotating propellers on all 4 engines. The Antonov An-22 transport, the Fairey Gannet anti-submarine aircraft, various turboprop airliners, all benefited from principles Smith proved viable. Modern turboprop engines powering military transports and regional airliners use concepts Smith pioneered. His work mattered, just not in the timing that would make simple storytelling. What this really teaches us: strip away drama and mythology, and lessons emerge that remain relevant today. First, brilliant engineering doesn't always arrive at convenient moments. Smith's solution was technically superior, but timing and circumstances didn't allow implementation. The best answer isn't always the answer you can actually use when you need it. This tension between optimal and achievable defines innovation during crisis. Smith created something revolutionary, but revolutionary technologies require time and resources that wartime doesn't always provide. The contra-rotating system needed infrastructure, training, and manufacturing capabilities that didn't exist in early 1944. Creating that infrastructure would have taken 6 months minimum, possibly longer. By the time the system could be in production, the war might be decided. Second, proving concepts and implementing at scale required different thinking and different resources. Smith excelled at the former, but couldn't control industrial and strategic factors preventing the latter. Laboratory success doesn't automatically translate to factory production. What works perfectly in one carefully assembled prototype may be impossible to manufacture in quantities of hundreds or thousands. The skills required to design revolutionary systems differ fundamentally from the skills required to mass-produce them reliably. Third, innovation during crisis involves brutal trade-offs between perfection and adequacy. The ministry chose proven reliability over technical superiority because strategic reality demanded immediate solutions, not optimal solutions arriving too late to matter. Sometimes good enough now beats perfect eventually. The conventional Griffon Spitfires had problems, but they were flyable problems that pilots could work around through training and tactics. The contra-rotating system promised perfection, but perfection that wouldn't arrive until after the critical moment had passed. Fourth, historical impact can be delayed and still matter profoundly. Smith's work didn't affect World War II combat directly, but influenced aviation development for decades afterward. The knowledge gained, the techniques developed, the problems solved, all contributed to post-war aviation in ways that continue to matter. The Tu-95 bomber that still flies today uses contra-rotating propellers. Modern turboprops benefit from aerodynamic principles Smith proved. Success isn't always immediate, and impact isn't always obvious at the time. Fifth, failure and setback are inherent to innovation, not exceptions. The first test revealed serious problems that nearly killed the program. Smith didn't give up. He analyzed data, developed solutions, and succeeded on the second attempt. That resilience mattered more than initial perfection. The willingness to face failure, learn from it, and try again distinguishes successful innovation from abandoned experiments. Smith's second test flight succeeded because he understood what went wrong in the first test and fixed it methodically. Sixth, accurate history matters more than entertaining mythology. The truth about Smith's work, with all its constraints, compromises, and complications, is more instructive than simplified stories of wonder weapons winning wars. Understanding why revolutionary technology didn't make it into combat teaches us more about innovation, manufacturing, and strategic decision-making than false stories of secret weapons ever could. If you made it this far, thank you for engaging with complex history, requiring nuance and accuracy, rather than simple mythology. This is what we do at History of World War II. We verify facts with multiple sources. We tell you when other channels are wrong. We don't take shortcuts. We do actual history. If that's the kind of content you want, subscribe now and hit the notification bell. Next week, we're covering another untold story from the Pacific Theater that most history books completely misrepresent. To everyone already part of this community, thank you. Your support, your thoughtful comments, your willingness to engage with complicated history, that makes this channel possible. And to those new here, welcome. Check out our other documentaries. Join the conversation. Help us spread accurate history. I'll see you in the next one.